Hi, this is Łukasz from EdgeDB and you're watching the 5th episode of Import AsyncIO, an introduction to the Python framework enabling asynchronous single-threaded concurrent code using coroutines. I know you've been pretty eagerly waiting for this particular episode, sort of like waiting for the next installment of the Song of Ice and Fire saga. And yes, it's becoming increasingly time-consuming to produce those episodes, so sorry for the wait. We've been also pretty busy producing the next alpha release, which currently is alpha 4 of EdgeDB. It's highly recommended for you to check it out. It's got plenty of improvements in ease of use and ease of installation of the database. But now we're here to talk about AsyncIO. So let's go with that. This series is intended as a beginner's course, so if you haven't used AsyncIO yet, that's perfect. Just start at episode 1 if you haven't seen this series yet. At this point, we are quite done with the basics and we can finally start looking at more high-level building blocks. So, well, almost, like here's the plan. We're going to start with 3 forms of asynchronous code support that are made on the language level. We haven't seen those yet, and we're going to start with asynchronous context managers. They are used by the async with block. Then we're going to move on to asynchronous iterators used by the async for block. And finally, we're going to cover asynchronous generators, which are the most advanced, but also the most useful of the 3. So all of those are pretty important for what's gonna come next, which is a big example showing what AsyncIO offers for networking, inter-process communication, and task cooperation. So let's start at the beginning. Let's imagine a database client, well, say EdgeDB. We use it to connect to a database. So let's provide it with some DSN, which is a data source name. And we can create a new object type when we do this. But before we do that, yes, we are now connected, and we are gonna take this connection, assign it to a value, and execute our object creation. What is that object going to be about? Well, it's going to be a user with a single required property, which is going to be a name, a regular string, and a non-required property, date of birth, which is going to be a local date. So having this particular schema selected, we can just execute this block. Done. The database now already knows of the user type. So now we can actually put some data in. So executing this insert, we will actually be using positional arguments right here instead of putting data directly as literals in the query. Like all proper databases do this. That will actually help you circumvent certain security issues. And also, actually is good for performance because we can now compile those queries for you and keep them regardless of the data that you're using. And speaking of the data, we are using my personal name and date of birth because at least the name is always good as a Unicode test. So let's now actually get that data back. Oh, cool. Looks like it works. So now we can disconnect. Close. Now, it's relatively easy to forget to disconnect from the database when you did all this, especially if you're making similar kind of fetch some data, change it maybe, show it somewhere else, flows. If you have many flows like this, it's sometimes just, inevitable. You're gonna forget to close. So that's hogs resources. So that's why in Python, we should be using context managers instead. We could then, kind of execute our select query like this. We will define a new context manager for our use to just see and kind of, remind ourselves how it works. We're going to be using a simple data class to hold the data source name and the actual database connection object once established, which is why it's optional at first. Like it's not established yet when you're creating the connection object right here. So now, the data class will deal with creating a dunder init method for us automatically, so we don't have to do this. So we can focus on dunder enter already, right? So dunder enter is the method that is called when the with block is, well, you guessed it, entered. We'll be creating a connection and returning it right there, right? So now the connection is no longer none, we actually have a real connection. Consequently, the dunder exit method is called when the with block ends or an exception is raised within it. So here we'll be just closing the connection object and returning false, which just means that we haven't handled any exceptions. So now we can actually use our new context manager and kind of do the same select as we did before. So select user and describe the shape. We want the name and the date of birth from the user. Let's run it. So, okay, same result. We're pretty happy with that. Now we know that every time we exited the with block, we will be free of any dangling connections. This works as expected in use, but if you looked closely, you probably noticed the lag in the with block's execution. The latency comes from three places. First, establishing the connection. Second, executing a query. And third, closing the connection. Out of those, establishing the connection is actually the most expensive. And I cheated a bit with the type annotations here. Well, there's no connection type in the EdgeDB package. Instead, there's a blocking IO connection, right? Like now this looks properly scary because we know each of the highlighted operations is actually blocking our thread. So we cannot use them. Instead, we will want to use some AsyncIO connection equivalent because we will want to use await expressions, right? So that AsyncIO can actually handle multiple connections, multiple customers, multiple whatever you throw at it. So we don't want any of those blocking operations. But wait, dunder enter and dunder exit methods are just regular functions. So we cannot use await inside them. And this is where asynchronous context managers come in. Et voila! Did you notice the change? It was quite sudden. First of all, we are using the AsyncIO connection type for our connection now. More importantly, instead of the regular enter and exit methods, we have enter and exit methods instead, and those are async functions. So thanks to that, we can now use await inside with asynchronous equivalents of the database client APIs. So we can see async connect and close right here. So for Python to know to use dunder enter and dunder exit, we need to use async with instead of just saying with. So we're doing that right now. So to see the result, we need to use asyncio.run right now, since it's an async function. Let's see how that's gonna go. So as you can see, it gives us the same result as the blocking version. But as you already know, with the magic of coroutines, we can now run multiple concurrent tasks in that same thread in a non-blocking manner. So in the real world, you will have a lot of asynchronous context managers, but you will rarely see them to make a single fresh connection to a database. Creating new connections is costly, as we've seen before, so it's best to create a pool and reuse it across your entire app. So typically this is done in some entry point that we're creating right here, and your actual user code is called later with past context. Right? So this is good because when your user code is done and we want to shut down the entire server, the context manager ensures that we will clean up all connections properly. So your user code, we're creating it right now, receives a pool object, and it can then use another async context manager to actually acquire a connection from it. So let's do that right now. async with db.acquire, and now we have a database connection. That allows us to query the database. So we can actually run the await to query, right, with the select we've been using quite a bit already. Like we don't have to actually make a fresh connection every time. The pool manages a few of them and just gives them to any new client that needs them for a while. And as the with block is over, we actually give the connection back to the pool. So when we run the entry point, we see that most time is actually spent creating the pool. You probably noticed when this was actually running. So this is worth it. We are doing this just once, and like later on, we already can use connections that are waiting for us to interact with the database. So moving on. Another fundamental protocol used for I/O in Python is iteration, right? You implement it by providing a iter method, which will return an iterator object. So iterator type, cool, of something. So in this example, we're just going to use bytes. Like some objects return themselves, like we are, while others have dedicated iterators. We'll see that as well. During actual iteration, using a for loop or using the next built-in, like we have calls to the next method on the iterator object now, right? So the purpose of the next method is either to return the next value or raise stop iteration, meaning I don't have any more values. As you can see, the read line in the example is this IO operation that is blocking. So in AsyncIO, we should be really awaiting on that. However, again, next is a regular Python function. So it's not an async function, and due to that, we cannot use await inside. So fortunately, we have a native async equivalent of this. And voila! It suddenly transformed to async def read line, and instead of iter, you have aiter, and so on and so on. So as you can see, the difference here is that like we will be awaiting on read line, and we have stop async iteration instead of regular stop iteration. Similarly, the entire aiter method doesn't return a regular iterator, it returns an async iterator. But as you probably noticed, it is a regular method. It's not an async function. Why is that? Well, its purpose is to produce a valid async iterator, which itself does not require awaiting on anything. If there's any I/O setup needed, that should happen during the first call to next. So how would you use async iterators in real life? One good example would be database queries that return large numbers of results. To demonstrate it, let's connect to Postgres this time. We'll be using asyncpg, which is pretty fast. You should use it as well. Similarly to the EdgeDB example before, we'll be using an entry point, which creates a managed connection pool to our Postgres instance. You will probably recognize that the API is very similar. It's because it's kind of by the same people, but also it tries to popularize the same kind of approach to database clients. So we will be delegating to print all users once the pool is created, and to print the users, our handler function will need to ask the pool for connections. So how will we do this? We'll use async with, kind of like we did with EdgeDB in the previous example. Having the connection, now we can actually run queries. However, Postgres requires using transactions for using cursors, which is what we're going to be using for our iteration example. Async for record in concursor. So we're selecting all the users and printing them. Again, using the async context managers for all of those is just a good idea, because we will release the connection when we're not using it anymore. Now, Having all this, if you counted it, we already are actually 3 ACMs deep at this point, right? We had this connection pool was created, and from the connection pool we acquired a single one, and then we opened a transaction. 3 async widths deep to just do something relatively simple, which is to output a bunch of records. Well, but you can see the magic right there. It is managing the resources for you properly, so it's worth it. Finally, we got to our async for, and we ran this select statement. So I only put a handful of records here, but I promise you this would stream nicely with huge result sets too. And the important thing is not only that we would be nicely iterating and the latency would be low, but also that we would not be using too much memory to do it. So now, in this video series, we never shy away from looking at how things are built under the hood. So let's look at the implementation of the cursor. In asyncpg, it lives in asyncpg/cursor.py. It starts off with a connection resource, which returns a cursor. That's the object returned by the cursor method of an asyncpg connection. We can await on it, but we can also use it in async for directly. For that, it's got a dunder iter implementation that we're looking at right now. So the implementation here uses the advanced form of dunder iter, returning a dedicated async iterator, not just self. So let's look at that iterator. Clicking through, we reach a class initialized with a deck buffer. Oh, that will become important in a second. Curiously, it also has its own dunder iter, but as you can see, it just returns self. But the money shot is actually below, right? Like we wanted to see what is happening when we iterate. So dunder a next. As we can see here, there's quite a few awaits, but the interesting ones are those that extend the deck buffer. Once that's done, dunder a next returns the oldest element in this first in, first out buffer. That makes the implementation very efficient. We can fetch multiple records at the same time, but still present them to the user one by one, just as if they were fetched from the database one by one. But unlike regular fetch methods, we are not fetching all the records at the same time. That decreases latency, as I already mentioned, because the time it takes for user code to see the first result is greatly decreased, but also saves a lot of memory, right? So win-win. Remember our reader async iterator? We could more easily define it in generator form. So an async generator will be what we'll be using exactly. So let's call it read, which is a verb, perfect for a function name, an async function to be exact. We also want to use awaits inside. And now, read, as you can see in the signature, takes a single argument, another async function, read line, and the code is just a simple while loop, right? It's essentially the code is shorter than the signature of this function. Like in the loop, we yield values as long as the value returned by readline is not empty. If you're a little confused by this colon equals, it's our new assignment expression added in the latest version of Python. Like this is a good example where it actually shortens the code needed and makes it clear to understand. So now, I already mentioned that we really waste more lines on the types in the function signature than the actual code. Like, isn't that atrocious? Well, no, like we are being exact about the types here. Like, and if you're confused by those, don't worry. We'll unpack this right now. So first, the type of readline is a callable which returns something that can be awaited on. So when that something is in fact awaited on, it will return bytes. That's what that entire read line of callable that returns awaitable of bytes means. So in plain English, we want an async function with a return type of bytes. It's the same thing. We're just using the notation of types. So now the async generator is itself an async function, right? So when called, it will return an iterator, an async iterator to be exact. And when that async iterator is consumed, it will be returning bytes. So those are the types. Instead of saying async iterator, we could have said async generator, of course, but it's quite a bit more busy. As you can see, now there's a none next to our bytes return value. As you remember from previous videos, in Python you can also send data into a running generator. So we have to spell it out, like what is the thing that you can actually send into. Since this generator doesn't actually do anything with data that's sent to it, we say none. But at this point, we could have just said async iterator instead, which is just as good. So we do that instead. To reiterate, the type of read is a regular function. That function produces async generator objects when called. So those objects look very similar to both blocking generators and async iterators. You'll find dunder a iter and dunder a next right there, as well as an asynchronous ascend and a throw. But I highlighted a close for you because it's an important piece of the puzzle. Let's look at it right now. Remember our print all users async function, which we defined a few minutes back? Now I give you the same function, but instead of printing users, it yields them. Yes, it's an async generator. So now, like any other async iterator, async generators can be used in async for loops. So we're gonna write an entry point in our application, which will create a connection pool and iterate over our async generator, but with a twist. Let's see how that will work. So async for record in generate all users. And we are happily now printing out the records. But if the record name is EL James, we are pretty much done. So what is happening here is we are performing a partial iteration and then we break out. This works. We can easily check this. Let's run our entry point in AsyncIO run. And we see that in fact, now we have fewer records that were printed out and we cut it short. So it's a valid use of iterators after all, right? Scrolling up, take a look at our magnificent asynchronous context managers. They have asynchronous jobs to do when the code exits them, right? They want to await to commit transactions, and they want to await to release database connections to the pool, and so on. So there's plenty of work that is there to be done when we are finished with the logic inside an asynchronous context manager. However, what will Python do when the gen all users object is now not needed anymore, when the async for loop is broken? Well, Python will garbage collect that object pretty much immediately. That's how scopes work in Python. So, well, that doesn't sound too good, does it? Because we needed this still for await to be done, for AsyncIO to actually run through it quite a while yet with its event loop, because we wanted to nicely commit a transaction and return a connection to the loop and so on to the pool. So this is problematic right now. And this is where that a close async method that I highlighted before comes in. When a close is called and awaited on, it interrupts the async generator and throws a generator exit. And then calls a next on that generator until it either sees generator exit or stop async iteration, which pretty much means, oh yeah, we now actually exhausted the async generator. That solves the problem of committing or rolling back, releasing resources, and so on. But we don't actually do this a close anywhere here, right? Like we don't await on it. So did we actually run it? Like, is everything terrible or are we safe? Well, in our typical fashion, let's look at the source code to find out. In AsyncIO, in CPython sources, in base events py, we want to find run forever. It's somewhere there. Oh, cool. We found it line 583. Since that method is also used by run until complete and in consequence by asyncIO.run. Inside we see get async gen hooks and sys.set async gen hooks. Those functions allow AsyncIO to be notified when a new generator started being iterated over or is about to be garbage collected. Thanks to this, AsyncIO keeps track of all async generators, and for those that need cleaning up, it indeed schedules a task to do it with a close, as you can see on line 519. So we can now sleep, safe and sound. Again, we don't have to worry. Actually, AsyncIO is doing everything correctly for us to make sure that asynchronous generators are finalized with returning resources. Everything is good. So asynchronous generators actually have quite a few use cases. We use them if you would otherwise write an async iterator, but you are overwhelmed by the amount of lines that you have to write, right? You have to create a class and create a iter and create a next. Very often an async generator is simply shorter. But if you need to handle context that needs to be cleaned up, like those transactions, it's way easier to do this thanks to a close in an async generator than to actually manage this manually in an async iterator. If you interface with publisher subscribers, async generators can also help you because they just yield values and you can use plenty of your own custom logic inside them. And finally, if you want to show your API as a nice publisher subscriber, but in fact you are forced to pull some particular resource, you can do this with async generators pretty easily. You can also filter incoming data. So if what you're already using is an async iterator or an async generator, it doesn't really matter if you're just using async4 on it. But you want to also do a bunch of other awaits to, for example, determine if your user is an administrator, which requires another query. It shouldn't, but maybe your database requires 2 queries for that particular thing. Or maybe you're using some stateless API like HTTP, whatnot, in which case, yes, those are probably gonna be 2 calls. This is actually pretty good as a way to filter and provide a single nice iterator for the user to iterate on. We can also aggregate, which is the opposite, right? Which means you are actually pulling multiple pieces of data, but then you do a thing to them and only give one thing back to the user. In async generators, this is easier to model than with asynchronous iterators because your state is just the local state of the generator. You don't have to play with object state to model this. So now I would like to show you a real-world example with what AsyncIO has to offer. This is going to be a working server-client application written in AsyncIO without any significant use of third-party libraries. We'll be building a very simple chat text-based system We'll be building it step by step, but I won't be typing all the code laboriously anymore, because like that would just take too much time this time. Remember that you can always just pause the video to look closer at a particular piece of code. So instead of typing, we'll be looking at 8 stages of the program's evolution, both in source form and in practical use. Let's dig in. So, boom. This is Visual Studio Code, and you're looking at the chat client.py file. That's the client in its simplest form. Note a bunch of things that I tend to do in modern Python code. So first of all, from future import annotations allows us to use a nicer notation for annotations with forward references and whatnot. I just use them, use that import everywhere. I do use star import for typing because it's simply very convenient to have those names everywhere. It's not going to be as prevalent in Python 3.9, where plenty of use cases for typing don't require special names anymore. But now, from typing import star, it's harmless, especially if you just put it exactly below the from future import annotations line. So that's the future imports. And now the star of the show here is a send file async function. What it does is it sends a file over the network to the server, line by line, and it prints what it received back from the server. So standard input, as you can see on line 25, can be treated as a special file. So that's good because we'll be using this in our interactive examples in a while. So the most important line here is line 9. Well, we open the network connection. So that's the star of the show. It's a built-in functionality of AsyncIO. So you provide some address you want to connect to, and you receive a stream reader and stream writer. They predictably allow you to read a number of bytes or send some bytes over the network. Reading is an awaitable operation, but writing isn't. That's interesting, right? Like you can just say write. To ensure all data was actually sent, you need to await on drain, which actually drains the buffer that you had. We are doing it in line 13. So for the for loop here exits when the file is done. So we read the entire one, or if a special command quit is found. We see this logic in line 17 and 18. That's the client. That was a little bit of talking, but it's because it's the initial thing. Like we're going to be iterating over that implementation soon enough. Let's look at the server now. The server is just as simple. I'm not showing you like the same kind of litany of imports that we've seen in the client. We are just looking at the handle connection, async function, and typical async main function as well. So let's start actually at reading the high-level main function. That will tell us what is our application doing when we start it. So we start a server by passing it a connection handler, which is an async function, and a network address pair. So then we, air quotes, serve forever. We know that it's never forever, but what it indicates is that unless there is an interruption, this is what this operation is going to be doing. Running any code below it is probably not going to work because there's going to be exceptions instead, right? So that's the kind of logic behind the name forever on this particular thing. So let's move on to the interesting piece, which is the handler. Handle connection, again, a verb, reads data received from the client. It uses 100 byte chunks, right? You can see this in line 11. It echoes it back to the client. So there's writer.write message in line 15. Right? So it's for now, our simplified code in the first iteration isn't really doing much chatting. It's just telling you back what you told it first. So as you can see, handle connection accepts a reader and a writer argument, and those are stream readers and stream writers. That is analogous to what we've seen open connection return in the client use case. So that is cool because the API is the same. So knowing how to interact with things as a client already taught you how to write servers in AsyncIO. So the interesting part here is maybe that we also have this special quit command, which causes the handler to stop reading further, right? That's essentially it. That means we're going to be closing the connection later. Simple so far? I hope so. Let's see how it works in practice. So let's start the server and let's start a client. We can type some things in, receive them back. We start a second client, receive things back. We start a third client, receive things back. As you can see, all the connections are now in an open state, so we can still continue interacting with the server. And finally, we can use our special command quit to just close the connection on both ends. So that demonstrates that the basic form works well, but we'll need quite a bit more for this to become a real chat application. What we want to accomplish is for the clients on the right to be able to talk to one another through the server, right? So not just with the server, which is just this boring star relationship. So let's change a bunch of things. But first, I would want to show you a particular reality of networking. We're looking at the client again, and I replaced sending the bytes from the file right away to the server with some rather elaborate logic right here. So we are sending 1 byte at a time, waiting 1/10 of a second before each write. Why would we do that? Well, in real code you wouldn't, but I'm demonstrating you network latency now. This is something that is going to be important to demonstrate some pathological cases of distributed systems. So we even print out that byte so we can see what was sent over the network. Like the hex number formatting is rather Perlish, I'm sorry, but at least it prints out nicely on the console right there. So the rest actually stays the same. So we can already use this with our server unchanged to see our system's behavior. So having the server already waiting for connections, we send bytes over. But now, hey, this causes the server to treat each byte as a separate message. That's bad, especially that now the special quit command no longer works. That's too bad. Fortunately, we can use Ctrl+D to indicate that the file standard input ended right on the client side, and that will force a closed connection on the client. Sadly, the server seems to be unhappy with such an abrupt connection closure. So, well, we're gonna have to fix that as well. So there's 2 things to fix. We're looking at the server again, and let's look at our while loop condition. Boom, I replaced the while with an async for right now. It used to be a symbol reader. Now we have an async for. We're using a split lines async generator. So this async generator is actually pretty simple right here. It accumulates data in 100 byte chunks, yes, but it looks for a new line character, and unless it was found, it just keeps accumulating. But once found, the message on the left of the new line character is yielded to the generator's consumer as a single message. So that's one of the use case I gave you for asynchronous generators in this slide that summarized what you can do with those. So look, we even handled the connection reset error that was upsetting the server before. But that line that we changed on the server side, that while reader.read, into an async.4 is the single line that we changed. The rest of the code stayed as it was. Let's see how that will handle the slow network environment right now. So with this simple change, the server composes the message from the received chunks, and all is well with the world again. Async generators to the rescue. Let's see if quit works. It does. That's pretty amazing. We're happy with this then. So it's not a chat system until the clients can talk to one another. To make this work, we need to ask newcomers to identify themselves. In this simple system, we won't be doing any real authentication, but we will take the user's name or nickname. Let's start by making the server ask. So we put this writer.write line 12, and that's the single change that we made so far. Let's see how that works. We already have a listening server, and now we connected 3 clients, but well, the client doesn't receive the greeting. Oh, it does, but only after it writes something itself. But that's not what we wanted. We wanted the server to talk to us first. Let's see what went wrong. Looks like the client code first reads a line from the file and writes it to the server, and only then it calls reader.read on line 21. So it kind of does this by design. And that assumption that we will not be spoken to unless we speak first, well, it's naive and doesn't work. So let's fix this on both the client and the server, since we have this design here and in the other file as well. So first, let's start by moving our smart latency simulation to its separate function in this helper chatstreams.py file. That way we can use it on both the client and the server. But if you squint, you see that this is the same Perlish printing and the same awaiting on sleep. That logic did not change. And indeed, we use the write helper function that we just moved in sendFile now, right? But more importantly, we made read handling a concurrent task. As you can see now, we create it as a task on line 21. That means the server can talk to us at any point, including before we started sending lines from the file to the server. So in handle reads that we have now above, just as in the server code before, we use split lines so that we handle network latency from the server too. That is important as well. So now we both deal with latency and messages of potentially different sizes, right? Like before we only had this rigid 100 bytes. What if the message was 102? Now this is all good. We also break on the special command quit. Cool. Now, another interesting piece here is what happens when the file is read in its entirety. We cancel the concurrent task and await its completion. That await could raise a cancel error, like we just canceled it ourselves. So we suppress it with the elegant context manager from context_lib. So we made changes on the client side. Now we're looking at the server side too. We replaced the inliner writes with this one-liner function that wraps the write helper in a concurrent task. So write soon is that thing. That means the writes will happen eventually. They will happen asynchronously. That's why in line 25, we will wait for all of them to complete before disconnecting, right? Like making sure everything that we wanted to say is actually written back. The rest of the code is as it was. Let's see now. The server is busily sending all the greetings to all 3 clients that were started simultaneously. But sadly, it looks like something is still amiss. The clients don't show the welcome message until they process the first line of standard input. Why is that? Well, the culprit hides in those two innocent-looking lines right here. See, this tiny for loop is indeed hiding blocking calls to readline on the file. So, blocking calls. If there was no line yet, the entire AsyncIO event loop was stuck. So boom, as you see already, to fix this, we are wrapping the blocking file using a nifty third-party library called AIO files. This is especially important for interacting with network-located files, which can have larger latencies than expected, and pseudo files like standard input, right? Which can have huge periods of time where nothing is happening because the user didn't type a new thing yet, right? So having this particular design with an async for, if you notice that, let's see how it works now. The server is sending the greetings, and we receive them now before typing anything. Full concurrency, just what we wanted. That's great. But that's not actually a chat yet. Fortunately, at this point, we are ready to fix that. We already dealt with some big architectural problems, and now we only need changes on the server side to enable chatting between users. So now we closed all connections. Let's edit the server py file. We need to be able to route writes between users. So we keep a global dictionary where the keys are nicknames and the values are their respective write soon functions. As you can see, we now handle more special commands besides quit. The I'm command in particular informs the server what nickname a given client connection should be known by, and the other special command is @ followed by a nickname. It allows a client to message another as long as they know their nickname. We even handle common error conditions like trying to message others without introducing yourself or trying to message an unknown user. An unknown user might be not connected at the moment, or maybe the sender made a typo. In any case, this looks ready for prime time. So, let's roll. Now we have to give our protagonists nicknames. So let's go with, say, Alice, Bob, that third one I forget. Okay. Look at this. You actually have to introduce yourself to speak. Alice did, so the message actually arrives, Bob. That's pretty cool. It kind of works. We can message one another, pretty nifty. We can even use rather unexpected features of this design, like, say, messaging yourself. That's kind of sad though, so let's try to cheer up Carl. Let's make Alice write Carl a message. Hey, you're fine, it's all good. And at the same time, we can also make Bob write to Carl. But look at this. Well, when multiple people try to contact Carl, we uncover another problem. The messages step on each other's toes, producing a joke-worthy concurrent word salad. Can we do better? Yes, we can. So we will be using a queue for this important task. The point here is that multiple sources can populate the queue, but there's only one consumer. Our handle writes async function that we see in line 36. The queue interface isn't very complex. The most important methods here are the get and put awaitables. We're using get here on line 40. There's a little added twist that if the message is empty, that signals that we should shut down. In the chat client, we refactored send file, making the network reader, the network writer, and the file copier concurrent tasks now. That allows us to make those three operations completely concurrent. And more importantly, it allows us to detect when we should be shutting down. So all of those are now concurrent. Thanks to AsyncIO wait and its return when argument, we can detect that either the file we were sending is completely read, or that we received the special command quit from the server, or that some source put the special empty string on the queue. So those are all nice changes, but the server also needs to fix the concurrent write situation. So we'll be doing this next. But for now, just take a look at send file again, seeing how elegant this design now became. We have plenty of concurrent things happening at the same time, but the send file function started being just a manager for those, creating asynchronous tasks and making sure that they are now all done properly and closed. So for the things that are done, we're fine with those. For things that are pending, we are canceling them and awaiting on them, similarly as we were before, suppressing cancelled error in turn. On the server side, we modified the user's dictionary to hold a write queue per user. We used the handle writes helper here as a concurrent task. We also did some important refactoring here, moving our command handling logic to a separate async function called handle commands. That refactor lets us notice that we should really be using try finally around the command handling, so that we always remove disconnected users and always close the connection gracefully. So the handle commands async function fits on a single screen. Let's click through it and see how that works. So not much actually has changed from the things that we copied over from the previous version. The most important difference is that we no longer have an awkward inner function called write soon. Instead, we simply use the queue API. So we await on put to send messages over, right? That happens on line 39, on line 44, on line 52, and line 57. But there's one more. Possibly the most important line, line 60, we put a message to another user in their queue. Let's see how that works now. Our protagonists introduce themselves as they were before. So I'm Alice, I'm Bob, and we remember Carl now. So I'm Carl. So now Alice, let's make her contact Carl. We can create some fake conversation right there. So we can even make Alice talk to herself while Bob has something to say to her too. So we're gonna now be sending a message to Alice. The server is still getting those, it's composing messages back, but we see Alice got them just serialized as we wanted to. Quit works again, all is good with the world. So we're happy with that design. This is actually the final version of what we're gonna be talking about in this particular talk. So maybe not very impressive graphically, but it was a proper distributed system right now. So pretty cool. And using AsyncIO pretty much exclusively, while barring that AIO files, which we only really needed here due to our simulation of interaction using standard input. So queues, that was the last subject right here that saved the day, and we used them in our example as a serializing funnel. So we had many producers, but only one consumer. Like in the industry, arguably the opposite use case is more popular. To have one producer, but potentially many consumers. So in this scenario, remember that a queue is a receive once data structure. Like if worker 1 got an element from the queue, worker 2 won't get to see that particular element. But it will likely get its own when it's available on the queue next. So while worker 1 is busy processing the first one, it won't ask for another one, and this is how all this cooperation is achieved. In this scenario, the queue enables concurrent task processing. More workers would increase throughput, so the AsyncIO documentation page on the queue has a nice minimal example of this particular use case. I won't be repeating it here. We already saw how queues work in our chat client server system. The last thing that I want to discuss today is synchronization primitives. We've already seen constructs that can be used for this purpose, like future objects in previous episodes, and queues just now. So the ones we'll talk about just the next slide over and a few others are following designs of the threading module. So those are battle-tested designs which you should use in two cases. First, when there is either data that is shared between coroutines which could be corrupted by free-for-all random access. And second, when you need to ensure ordering of events in your application. For example, you need to ensure your server is up and running before you connect some expensive resource to it. So fair warning, while the designs of the APIs we'll be looking at have clean, designs, concurrent synchronization is a tricky subject. So there's plenty of opportunity to shoot yourself in the foot. The first thing that we're going to be looking at is the lock. Once a given coroutine successfully acquires a lock, subsequent attempts to acquire it will wait until the first one releases it. So there's pretty much this async with lock API that you should be using. That's pretty much all you need. As you see, async context managers all the way. There's also a method that is called locked, which returns a boolean, which just signifies whether a particular lock is currently held by some coroutine. But there's very few use cases for that besides logging, because polling for locked is not a correct application in terms of atomicity. So pretty much the simplest use case right here is the correct one. Please use that. Note that none of the methods that we're looking at have timeout arguments. That's true for other synchronization primitives as well. It's because supporting timeouts is a built-in feature of AsyncIO. You can simply wrap whatever you need in await for, and it'll be fine. Apart from queues, events that we're looking at right now are probably the simplest form of communication between coroutines. One coroutine signals an event, and other coroutines wait for it. It's essentially a single flag that you can use in your program. There's also a clear method that pretty much unsets the event, and again, a boolean returning isSet method, but you should be wary of its atomicity. So it's mostly for logging purposes. Please use the simplest API possible right here. Of course, with this kind of is a thing set, which is called wait for this API, we cannot really use an async context manager because there's nothing to return on exit. So it's simply an await on the waiter side. And on the set side, it's not even an awaitable operation. It's simply a regular function. Semaphores are like locks, but they allow for more than a single coroutine to acquire it at a time. So it's like a maximum occupancy check, which allows for controlling load on restricted or expensive resources. So the biggest difference there is that when creating the semaphore, you decide on a concurrency level, right? Like the value might be 10, like in those examples from the docs, saying, hey, we will allow for 10 particular coroutines to acquire the semaphore at the same time. And finally, I saved condition for last because that's the most complex. It's also not used very commonly, but when it is, it's because queues were insufficient. That's interesting, right? Like in events, you have two sides of the system. There's some producer and some consumer. The producer acquires the condition object, produces some item, and notifies one or more consumers using the notify or notify all methods. On the consumer side, the consumer acquires the condition object and awaits on a notification using the wait coroutine, which is similar to what we did with events. So you wait on the condition, and in consequence, the producer calls notify, and the and the consumer's wait is done. So why would you use this? When there is some shared resource that needs a lock to access, but the lock is insufficient to determine if the shared resource is in a usable state for you. So in that particular case, the condition allows for some processor to signal that, hey, not only you just hold a lock right now, but it's safe for you to read or write to a particular resource. But if you look closely, there are ways here now to notify more than one receiver at one time. So that's again something that the queue implementation will not allow you to do. So that's pretty much it. Surprised we didn't do any examples with the synchronization primitives? Well, look at the duration of this video. Like in practice, you cannot really do too much in one go, but more importantly, we don't really use synchronization primitives that often in AsyncIO. That sounds blasphemous, but well, even when we do, we need to be careful. Synchronization primitives is where the ugliest or the most hilarious bugs are hiding. You can have ordering issues like race conditions and deadlocks. So to give those justice, I would have to make a special episode just about that. But the most important reason we don't really use a lot of synchronization in AsyncIO is that AsyncIO is not a computational framework. It's centered around non-blocking I/O, and computational heavy tasks defeat its purpose, since computation would necessarily block the event loop on a thread that now cannot react to other events and cannot call other callbacks using its event loop. So in AsyncIO, we often offload computation to other processes, and there's clear ways to do this, and there's clear ways to communicate with those other processes. We'll be looking at this particular problem in episode 7. Speaking of the plans for next, let's look at the schedule right here. We can now start building applications and produce examples that will be increasingly more interesting. In particularly, I'm excited about this next one. The episodes so far were rather encyclopedic summaries, right? Like we were talking about what's available and how it works. It was interesting when we looked at how it's implemented using its actual source, but it was pretty gentle and time consuming so far. But now's finally the time to tie it all together. So we'll be doing that with an example Starlet web application. We'll be using EdgeDB as the database for that as well. Subscribe to make sure you'll get notified when that is out. Well, when is it gonna be? I hope soon. Thanks for watching. See you next time.